right, thank you. So I'm going to frame my talk on who I am and what I'm passionate about, not by my previous research, but by the tools that I help develop and use on a day-to-day basis. So most of my work that I've done for the past 10 years has been geared towards supporting programs and tools like ParaView and Visit. I'm personally very heavily involved in the research and the development of the ParaView project. I'm not personally involved with Visit, but I do know that some of my work actually does make it to that project as well. What we're most focused on is what we call scientific visualization. We do a lot of analysis from simulations of physical problems. My personal specialty is in large data and parallel processing. And so here's just some eye candy of what we've done in some projects we've done in the past. And you can see that we work on a large amount of scientific domains and a lot of different types of visual processing. Here's an animation. Oh, it does work. Okay, here's a recent one of the Chelyabinsk meteor that just exploded over Russia. This is a simulation done at Sandia by Mark Boslow. One of my colleagues has been taking the data from ParaView and actually incorporating some Hollywood effects that provide really engaging visualizations that not only educate but also help garner a lot of interest in the work that we're doing in the national laboratories. And so, well, I'm going to skip this slide. And so now the next question we get to is that what are our challenges now? And most of the work and the research that I do now is garnered off of several recent workshop reports that talk about the doom and gloom of the upcoming HPC systems and how it's going to basically invalidate all the code that we're using right now. I'm personally working on two major problems that this brings up. The first one is this explosion in the number of threads and concurrency that we're dealing with on these new HPC systems. And so we can see it in these statistics from the last two supercomputers at Oak Ridge National Laboratories. The number of cores has gone up fairly modestly, about what you'd expect between two generations of supercomputers. But the amount of concurrency that you need to actually drive these at the highest rates has gone up phenomenally. And it all comes down to a different type of processor that we're using. So here, if you actually look at the two different processors, on the left we have the classic x86 architecture. On the right we have an accelerator like that being developed by NVIDIA. And each one of these have highlighted what a core looks like. Now the core in the x86 architecture, as you can see, is fairly large and it's complicated. It has about 20 years of research and development that makes your programs run faster no matter how you do them. Now the core on an NVIDIA accelerator is a much simpler device. It's basically just a collection of accelerators. It doesn't even have its own control logic. It's shared among several cores. And so not only do you need a lot of extra concurrency when you're running on these devices, but you have to structure your parallel code to be very careful to make sure that you run these at maximum efficiency. And so there's a lot of challenges that I don't have time to go through in order to get your visualization to run effectively on these systems. But suffice it to say that there's several projects within DOE geared to solving these problems. I'm currently leading a project called DAX, which not only is addressing these issues, but also trying to build toolkits to make it easier to develop in this environment. The second problem that I'm most focused on is this continuing disparity between the computation rate of these systems as well compared to the storage system parameters. So on this slide, I've collected statistics from leadership class facilities of 4 different national laboratories, which comprises a fairly large proportion of the overall supercomputing power in the world. And you can see a disturbing trend that with each successive generation, we're getting about an order of magnitude more improvement in the system peak execution rate than we are in the bandwidth to the I/O systems, which means that for every subsequent generation, we can run out a smaller and smaller fraction of the data that we're computing. Now, this is a serious problem because the workflow that we typically do within scientific analysis is that we'll run a simulation independently. It will compute some results, which tend to be fairly large, and store them on a storage system. And at some point later, visualization will read that off of the disk and do the analysis. Well, it's inevitably going to come to a point where you're not going to be able to write enough data to your storage system to do the proper analysis. And so the obvious solution is that we have to move the visualization closer to the simulation. So one of the projects I'm working on is called the Catalyst In Situ Library. Basically, this is a library that simulations can use in order to directly call the parallel visualization services that we already provide under the ParaView project. And so we are taking the Catalyst library and integrating with several different simulations. It's supposed to be an animation, it's not playing. Here's some examples of doing of coupling with CFD codes. Here's another couple of examples, if slide will actually advance. There it goes. Once again, an animation that's not playing, but some shock physics code, Earth's magnetosphere. If the animations you were playing, you would see that by coupling the visualization with the simulation, you can get a much higher both spatial and temporal fidelity than you could otherwise. All right. So finally, hey, I'm actually pretty good on time. So finally, the question is what are the wish lists that we have? What are no, now I've wasted it. What's our wish list what's our wish list? And it's not so much what can we do in visualization, but is what are the missing things in what's missing in the HPC community that would make my life easier? And so for one thing, I would really like an abstract I/O layer for job-to-job communication. So we have nice abstract interfaces to our parallel file systems, but as I just explained, they're getting too slow. I want to be able to pull information from other running jobs. I'd like to see improved HPC job schedulers. Our job schedulers were designed 10 years ago when things were very homogeneous. Right now we have heterogeneous architectures, heterogeneous jobs, and the schedulers need to take this into account. Finally, it would be really nice as a pie in the sky to be able to run virtual machines in our HPC systems. That would simplify a lot of development, deployment, distribution, as well as open up a lot of avenues, not only in visualization, but elsewhere in HPC.